Okay, so welcome all. So after 2 years, I am giving the same course. So 2 years ago, I started lecturing differential geometry. At the end of the 6th week, we stopped, face-to-face teaching. We switched to online teaching. And since then, this is first time I will actually write on board. I will use my notes I prepared back then. I did only 1/3 of it in class. My notes and the videos I recorded 2 years ago are on my web page. I will record Zoom sessions also this year, and I will post them on YouTube also, but I will use the same notes. Okay. Actually, there are two sets of notes on the internet. One of them is the notes I wrote for myself, and the other ones are the notes for the videos. While I was recording the lectures I wrote on the screen, and those notes are also on the internet. But of course, first 6 weeks of the lecture notes or video notes are not there because we did face-to-face teaching for the first 6 weeks. After the 6th week, we switched to online teaching. Actually, not exactly that way. We waited for a couple weeks, and then we were told that we have to start online teaching. Okay, so what is differential geometry of curves and surfaces? Differential geometry is a huge subject of mathematics. It involves almost all branches of math, of course, geometry, topology, analysis, differential equations, ordinary and partial differential equations, algebra, all kinds of math is related to differential geometry. In this course, what we will do, we will study only curves and surfaces. And what we will do, for curves, we will define some invariants of curves, which will allow us to identify curves. For example, this helix, let's say, and I have another helix, let's say like this. And suppose that one of them is obtained from the other by just rotating and shifting. If I gave you the mathematical equations for this, there is no way you can guess from the equations that actually these are the same curves, just rotated and shifted in the plane, in the space. What we will do, we will define basically two invariants, curvature and torsion, for this kind of curves, space curves, and we will compare those invariants. And for example, for these two curves, we will see that those invariants, curvature and torsion, are the same for both of them. And that will imply that this curve is obtained from this curve by just rotating and shifting. So we will define basically torsion and curvature. Curvature, what was the, I guess, what was the notation for the curvature? Yeah, kappa. Okay. The idea is simple. Suppose you're in a car and you have a you are blindfolded, so you don't see anything, but you feel how the car moves, whether it goes straight or it turns, or it accelerates or brakes. Suppose you can measure the acceleration, okay? And if you know the acceleration is a function, and if you know the initial position and the initial velocity of the car, then you can determine all the journey as a function of time by just integrating. The idea is basically the same, okay? Curvature will correspond kind of the second derivative, how the curve is bending, how the tangent vector is bending, and torsion is another measure which shows how the curve bends in 3 space, kind of. So torsion itself is not enough to determine the to determine the curve. You need also so-called this torsion, and these two invariants will be enough to determine the curve. Okay. So this will take like 6 weeks of our lecture. In the remaining time, we will define surfaces. So this is the curves stuff. First, we will study curves. Okay. Basically, space curves. And in this second half, well, actually, it is more than second half. In the remaining time, we will study surfaces in the space. What we mean by the space in is R3. Okay, we will study surfaces in R3, and that again we will have some invariants which will show us how the surface looks like, and whether two surfaces are essentially the same or not. And the basic invariant will be again curvature. Actually, we will study mostly Gaussian curvature. This is introduced by Gauss, okay? And then his student, Riemann, took this study and he generalized to all dimensions. Well, actually, he created the study in all dimensions and generalized Gauss's work, so that we still use his actually conventions. I mean, he did such a great job to extend Gauss's work on surfaces to higher dimensional objects, which we call them manifolds, actually Riemannian manifolds. So since they are introduced by Riemann, what is curvature? Curvature is also an invariant of surfaces, and it tells us how the actual surfaces are again curved in space. For example, consider this plane. Belki şurada anlatmam daha iyi olur, değil mi? This is the plane and it is flat. Gaussian curvature of this is 0. Okay. You can bend it and make a cylinder. It is not flat anymore, right? It doesn't look like flat, but actually in the sense of curvature, it is still flat. Why is that? Because, you know, when you open it up, it just becomes flat, okay? So curvature for plane and for cylinder are the same, and it is both 0. So for us, a cylinder is a flat object, okay? When you cut it through an axis, it just becomes a piece of plane. Again, a cone, you know, something like this. So this doesn't look like flat also, but actually this is also flat because it is obtained from a actual flat surface by just rolling it, okay? So it is still flat. But the surface of a sphere, okay, is not flat. It has positive curvature. Therefore, sphere is something different than a plane or cylinder or a cone, okay? So we will see that Gaussian curvature is 0 for plane, cylinder, and cone. And Gaussian curvature is 1 over r. R mıydı? R square mıydı? Well, to be on the safe side, let me say it is yeah, it should be r squared, I guess. So it is positive for a sphere of radius r. Okay. So toward the end of the semester, we will see what Gaussian curvature, and we will use actually our study on curves to study surfaces, and we will use a lot of linear algebra. So linear algebra will be a very essential part of the study. Okay. One of the main theorems in this study of surfaces, which is my favorite, Gauss-Bonnet Theorem. Although it is called Gauss-Bonnet, neither Gauss or Bonnet actually stated this theorem. They didn't also prove it because it wasn't stated actually when they were alive. However, their work actually is enough to state and prove this theorem. So people realize that there is such a theorem. It's a global theorem, not a local result. Curvature is a local thing. You know, you can bend a surface or curve locally, okay? Or you can flatten, you know, you can make it flat locally. But the total curvature for a closed surface doesn't change, okay? Total curvature for a surface doesn't change. What we mean by that, what are the closed surfaces? Closed surfaces are things like this. They are kind of sphere, you know, look like sphere, but they have some holes in them. If you don't have any hole, then it's a sphere. If it's a one hole, then it is a surface of a simit. If you have more holes, then we call it a surface of genus G. Suppose this is the first hole and the second, and this is the Gth hole. So this is a surface of genus G, orientable surface of genus G. Okay, you can do this from dough, right? And even cook it and eat it. The theorem is this: if you integrate this Gaussian curvature over the surface, so Gaussian curvature at each point is a number. It can be 0, it can be positive, it can be negative. If you integrate this function over the surface, okay, you will get a number. That number is always determined by this G. It is just 4 pi 1 minus G. Okay. No matter how the surface looks like, it can be, it can look like this, but it can look like also like this. Let me see if I can switch to this board. No. No, it changes. You can change the local curvature, but the global curvature doesn't change. Or they are not diffeomorphism. That thing is not diffeomorphism. Diffeomorphism can change everything practically. Opening this up and making it flat is not a diffeomorph. I mean, it's a diffeomorphism, but it's a special one. Okay, it doesn't change the curvature. It doesn't change the geometry. A surprising thing about this is the following. Suppose you have a sphere, a huge sphere of radius, doesn't matter, whatever the radius is, let's say r. Then we know that the curvature at any point is 1 over r squared. And if you integrate this curvature over the sphere as 2r. So let's call this sphere of radius r. Well, this thing is a constant function. It is 1 over r. Since this is constant, I can take outside the integral. And here we have the area element evaluated, integrated over the surface. This is just the surface area of the sphere. So it is just 4 pi r squared. Okay, this integral 4 pi r squared, and the result is of course just 4 pi. It is consistent with this because sphere has no holes in it, in the sense of this kind of holes. Okay, it doesn't have any holes, so this is a surface. Sorry, this is a surface of genus 0. Okay, genus 0. So this G is called genus of the surface. Of course, I have to be careful, right? So G is the genus of the surface, and for the sphere, the genus is 0. Okay, genus is 0. So this integral is 4 pi. What this theorem tells us the following. Suppose this is the whole Earth. Okay, it's very big, and it is so big that this is very small. That's why people thought for centuries that the Earth was flat. Actually, there are still some people that they believe that it is flat, but we know that it is not flat. However, you can make it flat in the global sense. How? Well, just on a very small portion of the Earth, put an handle. What we mean by handle is put something like this. So a handle like this to the Earth. Okay, it can be very small. It may have size of a millimeters. It can be very small. Once you do that, your surface topologically becomes a torus. Now this is not a sphere. This is a torus. So this is the same thing as this one topologically. So its genus became 1. And this integral will turn out to be 0. Okay. So by just changing, putting a handle, a very small handle, makes the whole computation become 0. So once you do that and integrate it over this new surface, the result will be 0. Okay. So Gauss-Bonnet Theorem is such a powerful actually result. Burası anlaşıldı mı? Okay. So toward the end of the semester, we will learn about Gaussian curvature and Gauss-Bonnet theorem and many other things related to curvature and so on. Also, let me tell you something about kinds of geometries. This Gaussian curvature can be 0. In that case, we have so-called flat surfaces like plane or a cylinder or a cone, like this. These are all flat. And then we have surfaces with positive curvature. It's basically the sphere, okay? Or so if curvature is positive at a point, then it looks like a sphere at that point, okay? So we have sphere. And for surfaces with negative curvature, well, for a long time, people thought that such surfaces doesn't exist, actually. Actually, for a long time, people thought that all surfaces are flat. All geometries are just Euclidean geometries. Actually, Euclidean geometry is the only geometry, they thought. Then people realized that Euclidean geometry is actually one of the few geometries after Gauss and Riemann's work. We have geometry on a sphere, and the geometry on a sphere is a lot more different than the geometry on a plane. For example, on a sphere, the sum of the interior angles of a triangle is not 180, okay? It is larger than 180. But people didn't believe, this kind of thing would happen for a long time, okay? And there is another kind of geometry. So for sphere, of course, you know this, right? Let me check if I have. Well, I don't have color chalk, but so suppose you have this triangle. One corner is at the pole, another corner is a point on the equator, another point is also on the equator. So this angle is 90 degrees, this angle is 90 degrees, and this angle can be anything you want, right? It can be very small or big. So the sum of the interior angles is right, is pi plus whatever this alpha. Okay. What about surfaces like this? So these are elliptic surfaces. These are flat surfaces. And these are so-called hyperbolic surfaces. I cannot draw you a closed hyperbolic surface in R3 because we don't have any closed hyperbolic surface lying inside R3. But locally, a point where the curvature is negative looks like this. A saddle surface, okay? So a point like this, okay, if you measure the curvature at a point like this, curvature is negative, okay? Kp is negative. You may ask, okay, what's the surface where all the curvatures are actually negative, like the sphere, right? Sphere is a point, is a surface, so that at each point, curvature is positive. Is there a surface so that at each point the curvature is negative? Yes, there are the surfaces with genus larger than 2. So if you take a surface of genus larger than or equal to 2, so a surface like this, you can put a metric on this so that at each point it looks like this point. However, you cannot do this in R3, okay? You can put a metric on this surface so that at each point it looks like this. Curvature becomes actually -1 at all points. But you cannot realize this surface in R3, okay? You can realize it in some other higher dimensional space. Actually, I don't know at the moment, which dimension, but it exists, we know that. And that result is due to John Nash, actually. So he did some, very nice work on geometry of manifolds, in particular, Riemannian manifolds, and he showed that if you put an abstract metric on a manifold, in our case, let's say a surface, you can actually realize this surface in some Euclidean space, so that at each point the curvature is the curvature you prescribed. Okay, so okay. Yeah. Also, actually, for genus 1, consider this torus. For the torus, the integral Gauss this integral for this torus over the torus, let's say, we know that this is 0. So this suggests that I may put a metric on the torus so that it becomes flat at all points. Okay. And you can do that, but not in R3. We will prove as a theorem that if you have a closed surface in R3, there is always a point on the surface where the curvature is positive. For example, here, this point will be a point where the curvature is positive. At this point, the surface looks like a sphere, okay? However, at such a point, the surface looks like a saddle. Like this one, right? At this point. If you just think for a while, at this point, the surface actually looks like this, okay? There is one direction going like this, and there's also direction going like this. So you have a surface like this, surface piece like this, okay? And this point is a hyperbolic point where the curvature is negative. And it should be the case because the total curvature is 0. And there are some points where the curvature is positive due to Gauss. So for the integral to be 0, there should be some points where the curvature is negative. And there are this kind of points, okay, where the curvature is negative. But as I said, it is possible to put a metric on torus so that it looks like flat, okay, like cylinder, like the plane, okay, but we cannot realize it in R3. In R4 it is possible, but not in R3. Okay. So this will be kind of the introduction. Now, any questions so far? Okay, so let me switch to the board, let's say. Yeah. Okay. So let me start with section 1.1. We will first study so-called Euclidean space. I am following the book by Barrett O'Neill, Elementary Differential Geometry. I guess it is written on the syllabus, right? So the first thing we will do, we will see the geometry of R3 basically. Well, not the geometry, but we will set up notation. As I said, we will study curves and surfaces embedded in R3. So we have to understand R3 well enough. So what we mean by Euclidean space, let me explain it. Euclidean 3 space R3 is the set of all ordered triples of real numbers. Such a triple, let's say P1, P2, P3, is called a point of R3. Summation and scalar product are defined as follows. You all know this stuff, but it's better to review. So if we have, let's say, 2 points, P1, P2, P3, and Q is another point, Q1, Q2, Q3, then P plus Q is just the point where you just add the coordinates. And if you have a real number, A, let's say, then A times P is just the point. So this is A times P1, P2, P3, and this is just AP1, AP2, AP3. Okay. All right. Okay, I already told you you add the coordinates, but let us see the formal definition of what's a coordinate function. The coordinate functions x, y, z on R3 are defined as follows. So x is a function defined on R3 and takes values in R, and x of a point P1, P2, P3 is the first entry, P1. Y is another function. Y coordinate, and it gives us actually the second entry of the triple. And the Z coordinate function is the function which gives us the third entry of the triple. Okay, so these are the coordinate functions. So for us, coordinates are actually some functions on the set of points. Okay, x coordinate R3 is the set of triples, and x coordinate is just the first entry of that triple. Y coordinate is this value of the y coordinate function is the second entry, and z coordinate of the triple is just the third entry of the triple. Okay. Now, recall that we have so-called partial derivatives. Well, since this is a differential geometric course, we will take basically differentials, okay, derivatives. So this course is about taking derivatives and giving meanings to those derivatives of a function f from R3 into R are defined as follows. So the x derivative of the function at a point P is just the limit as h goes to 0, f of P1 plus h, P2, P3 minus f of P1, P2, P3 divided by h. Okay, this is the x derivative. Here, of course, P is a point in the space. It's a triple. Okay, let me erase this part. You may stop me anytime if there is anything you don't understand or you find confusing. All right, so let me switch to the screen. No, oops. Okay, I guess one of the buttons got stuck and it recorded one of these as the second board, but it should be this one. So I had to switch it. Okay, now the partial derivative of f with respect to y at the point P is similarly defined as the limit. Of course, these are defined provided the limits exist, right? If the limits do not exist, then of course the partial derivative doesn't exist. And finally, the partial derivative of f with respect to z coordinate is defined as the limit of this expression. Okay, provided that these limits exist. Okay. Well, of course, partial derivatives are also note that partial derivatives these are also functions. Right? Partial derivative of f with respect to x is a function, right? It takes a point to the partial derivative of f at that point, and so on. And since these are functions, of course, we may consider derivatives of these functions. So, namely, we may consider higher derivatives. Okay, şöyle yapayım. Bakayım becerebilecek miyim? Şimdi şunu şuraya alayım. Okay. And let me erase this part. All right. Now come back to second screen. Yes. Of course, one may define, other partial derivatives as functions. Similarly, we may define higher partial derivatives if they exist, of course. Okay. For example, partial derivative of f with respect to the variables x and y. So what we mean by this, now you have already this function, partial derivative of f with respect to y. This is a function, and I may consider the derivative of this with respect to x, right? And of course, there is no, reason you stop at second derivative. You may take higher order derivatives, and you remember that we use this kind of notation. For example, this will mean what? This is just partial derivative of partial derivative with respect to x of what? Partial derivative with respect to x of partial derivative of f with respect to z. Okay. Of course, all these gadgets exist provided that the limits exist. Okay, if the limits at each step you will take a limit. If those limits all exist, then we may talk about partial derivatives of f. And we have a definition. For us, a function will be differentiable if all partial derivatives exist, okay? If, so a function f from R3 to R will be called differentiable if all partial derivatives of all orders exist. So you are given a function, you take first order derivatives, and then if they exist, you take second order derivatives, and then third order derivatives, and so on. if you can do this for each integer, in other words, if f has partial derivatives of any order, then we will say that that function is differentiable. In some books, that's also called, for example, C infinity function or smooth function. Okay, C infinity smooth function in our case will be just called differentiable function. But there are some text where you may find different kinds of naming. For example, there are functions which is differentiable, let's say 5 times, but 6th derivative doesn't exist. In that case, we say that function is of class, let's say C5, meaning that it is 5 times differentiable, but not necessarily 6 times differentiable. Okay. Imply what? Yeah, sure. I mean, if it is differentiable once, then it is continuous. Well, actually, what I said is not maybe true. Existence of first partial derivatives doesn't imply that function. No, well, yeah, it doesn't imply that the function is differentiable. But existence of second derivatives, and here, since I assume that all derivatives exist, it means that actually all derivatives are also continuous, and therefore actually function is itself continuous, right? For the, yeah, I mean, we assume that all partial derivatives actually also differentiable, and that implies, I guess, continuity. Yeah. Okay. Let me give a break. Şimdi kaydı durduracağım ama nasıl? Kaydı durdur.